everyone, and welcome to another video. I know it's been a while, I'm really sorry about that, but I was just facing some issues with my laptop and I was just working on so many things. I was too busy to record the video, but here we are now. We are going to continue exactly where we left off in the last video. We are going to continue with electrolysis. Today we're going to talk about the extraction of aluminum, which is a process that's also known as Whole Herald process, which, if I recall correctly, was a German scientist. And just a quick reminder regarding the aluminum, as that's going to be the king of our conversation today. If we take a look at the periodic table real quick, we will see that we have aluminum right here in the periodic table. And we do have 13 electrons, which is the electronic distribution of aluminum. So if we want to write down the electronic distribution of that element, it's going to be as follows. So we have 2 electrons in the K, 8 electrons at the L, and 3 electrons at the M. And those are the 3 electrons that aluminum uses to donate electrons to contribute in chemical reactions and form the um, aluminum cation, which is, as we know, Al3+. Okay, so this is very important for us today to know the electronic distribution and how aluminum contributes in chemical reactions. Okay, so back to our topic, which is the extraction of aluminum. Aluminum is actually the most abundant or redundant metal in the Earth's crust, and it exists in a form or in an ore called bauxite. And if we can just get back to the notes real quick here, bauxite is actually like a mixture of aluminum, Al2, aluminum oxide, Al2O3, with some water and a whole bunch of impurities like silicon dioxide. And the most important impurity that we have would be iron oxide, Fa2O3. All right. So in order for us to extract aluminum from bauxite, and by the way, I don't really need to know this formula by heart. I'm just giving it to you for general knowledge. We need to do a couple of things. First off, we need to get aluminum oxide in the form of a soluble salt, and we need to get rid of the iron oxide, right? In order for us to do that, we tend to react the bauxite with sodium hydroxide, which is, if we recall it correctly, was NaOH. Why we do that? In order, as I said, to get the aluminum in a soluble form. And that soluble form is called sodium aluminate, or NaLO2. I know that might be a strange formula that you are not really that familiar with, but it's actually pretty basic if we take a look at it. Like, for example, if we take a look at sodium, give me 1 second, here we go, sodium aluminum oxide, or sodium aluminate. So if we break this into 2 sections, right, a cation and an anion, we will see that the oxygen here contributes with 2 electrons each. So we have 2 of them, so we have a total of -4 charge. And on the other side, we have our cations, which do contribute with positive charge. So each aluminum, as we've agreed, is contributing with 3 positive charge. So we only have 1 aluminum. So we have 3 positive charge. And we also have the sodium. And if we recall correctly, the sodium, if we get back to the periodic table real quick, was Na11. The electronic distribution for that was 2 8, 1. So it's only contributing with one positive charge. So if we get back here, we have one positive charge. If we add together the positive charge, we will see that we have 4 positive charge and we have 4 negative charge. So the net charge on this compound is 0. So it's just like sodium hydroxide, like copper sulfate, like any other stable compound, we have a net charge of 0 on that compound. If we um, divided into cations and anions, the negative charge is equivalent to the positive charge, so the total charge at the end of the day is 0. All right. So how did we get here? Again, we had bauxite, which is the aluminum ore, which is a mixture of aluminum oxide with some impurities like iron oxide. We reacted that with sodium hydroxide, which is NaOH, and we ended up getting sodium aluminate, which is NaAlO2. The important thing or the important characteristic about the sodium aluminate is that it's a soluble salt that does not react with iron oxide. And if we also recall correctly, hematite or iron oxide is actually that's a terrible color. Give me 1 second. Pick something that should work. Yeah. Iron oxide is an insoluble salt, which means that we can separate it by filtration. If we are separating an insoluble salt from a liquid or from a solution, we use the filtration method. And you can always get back to chapter 2, the video for chapter 2, separation techniques, and you will find more details on the separation techniques, filtration, and all of these things. Okay. In order for us to refine the sodium aluminate even further, we tend to chemically treat it with carbon dioxide. We don't really need to elaborate much on that part, but it's just for your knowledge that we actually tend to chemically treat um, um, sodium aluminate with carbon dioxide in order for us to get a more pure form of aluminum oxide, which is Al2O3, which is what we have been looking for all that time, actually, Al2O3. In fact, we are not really looking for the aluminum oxide, we are actually looking for the aluminum itself. But aluminum, as you can see here, is extracted from alumina, which is the another name for the aluminum oxide. The problem with alumina, though, is that its melting point is around 2000 degrees centigrade, which when you think about it, requires too much heat, too much energy for us to extract aluminum. And when you think about it, aluminum isn't really that expensive. So how come it requires that much energy and is not really that expensive? So to answer this question, the secret lies in kaolite. So what is kaolite? That's a new term that we are dealing with today. Kaolite is um, it's that compound that is actually used to reduce the melting point of the aluminum oxide. The formula for kaolite is actually Na3Alf6. Let's break that down real quick. So let's just take a look here at kaolite. So get rid of these unstable elements. All right, so when it comes to kaolite, as I said, the chemical formula for that would be Na3Al if for fluoride 6, just as we did with the sodium aluminate or the sodium aluminum oxide. We're going to break this down into cations and anions to make it easier for us to understand this compound. So if we go ahead back to the periodic table real quick to check on fluoride, because we have already checked on aluminum and sodium, so let's go ahead and check on fluorine real quick. We will see that we have fluorine right here. I can't find the cursor. Give me 1 second. Let's pick a color. Here we go. So this is fluorine. Here it is. Okay. Yeah, we can find it. So that's F9, which means that its electronic distribution would be 2 and 7, because 7 plus 2 equals 9, which is the total number of electrons that we have in here, which means that fluorine, when it reacts in a chemical reaction, as a member of the seventh group, it tends to gain an electron because it's easier for the outer electronic shells to just gain 1 electron to have 8 electrons here. So fluoride just tends to gain 1 electron in order to form the fluoride anion. Okay, so that would be F negative, because it will be gaining 1 electron to be put right in here, so that we would have 8 electrons in here, so that it would stabilize, and the outer shell would be completely saturated with electrons. Now, how did we get here again? Karyolite. We just a quick recap, we had bauxite, which is the aluminum ore, which had iron oxide. We wanted to get rid of the iron oxide, so we reacted the bauxite, which is the aluminum ore, with sodium hydroxide, and we got sodium aluminate, which is this thing right here. Here we have it, sodium aluminate, or sodium aluminate, and we broke that down. And then we removed the iron oxide with filtration. We got further chemical treatment for the sodium aluminate with carbon dioxide in order to get aluminum oxide, which is Al2O3. So we reacted the sodium aluminate with carbon dioxide, got aluminum oxide, which is also called alumina. Now, alumina has an issue, which is that its melting point is around 2000 or over 2000 degrees centigrade, and that requires too much heat and energy. So we use karyolite. Karyolite is just that compound, which is sodium, aluminum, fluoride, this guy right here. And the whole purpose of that is that it actually does 3 things mainly. It lowers the melting point of alumina to around approximately, give me 1 second, I like messing around with colors, around 900 degrees centigrade. I know that's still way too high, but when you think about it, from 2000 degrees centigrade all the way to 900 degrees centigrade, that's like half the temperature, if not even more. So that lowers the melting point, hence saves energy, and it helps with electricity conduction as well. So what do we benefit from that? What's the benefit of karyolite? Lowering melting point, saving energy, and helping with electricity conduction. And the electrolyte that we use in the extraction of aluminum is actually both molten aluminum oxide and karyolite, because in order for us to melt the aluminum oxide, the Al2O3, we need karyolite in order to be able to melt that at reasonable temperatures. All right, so back to our notes real quick. We're just going to take a look at the cell here before we dive deeper into the half ionic equations and all of that. So as we can see here, we've got an anode and a cathode. So the most important thing that we need to notice out of all of this is that the anode and the cathode, both of those are made of graphite. And if we recall correctly, graphite is just carbon, right? That's important to us because we're gonna we're going to have to comment about that in a few seconds. And it's graphite. Remember when we talked about electrodes, they were usually made of either platinum or graphite. Why? Because they do not really react with the reactants or the products of the electrolysis. However, in this case, in the whole Herald process, we are using graphite. We're not using platinum, so we can just go ahead and erase that platinum out of here. It's just reminding you of electrodes. And this is a siphon where we get the aluminum out, and we have the crust of um, the crust solid electrolyte, which, as we agreed, is actually cariolite in a Al 2 F6. Give me 1 second. In a 3 AlF6, as we've agreed, and that's the cariolite with the molten alumina, which is the Al2O3, as we've agreed, which is the aluminum oxide. So get used to writing down the chemical formula for the sodium aluminate and the cariolite, because I know that those might seem like new formulas for you, but as we've broken them down, they are not really that complicated. Okay, now let's get to our half ionic equations, because this is electrolysis, this is electrochemistry, and we can't live without half ionic equations. Let me just go ahead and erase the stuff real quick, and let's see what we have here. All right, so we've agreed that we have an anode. We also have a cathode. The anode, as we've agreed, has the oxidation, while the cathode has the reduction reaction. Okay, so that's a redox reaction because it has oxidation and reduction. Now, at the anode, as we've agreed, we have the oxidation, and oxidation is actually a loss of electrons, while reduction is actually gaining of electrons. All right. So what is the compound that's actually reacting in this reaction? So the compound that's actually reacting in our reaction here is aluminum oxide, which is Al2O3. If we break this down into cations and anions, we will see that we have a total of, give me 1 second, let's do neutral. Okay, we have 6 electrons in here, 2 multiplied by 3, negative 2 multiplied by 3, so we have a total of 6 electrons, and we have, let's pick a nice color, and we have also positive 6 charge in here. So I meant 6 negative charge, and we have 6 positive charge, 3 multiplied by 2, because each aluminum is contributing with 3 electrons as we've agreed, and each oxygen is gaining 2 electrons as we've agreed. So we have total, or the net charge on this compound, as 0. Now, which one of those would be gaining electrons and which one would be losing electrons? Basically, the one ion that has a redundancy of electrons would be the one that's actually losing the electrons. So that would be the anion. And in that case, that would be the oxygen in this case. All right. So here we have the O2 negative, and that would be the oxygen. And here at the cathode, we would have the cation, of course, because it will be gaining the electrons, right? In order for us to be able to continue the half ionic equations, let's just agree that for this reaction, just to save you time, we need 12 electrons. You can go ahead and do the math, you can calculate it yourself, you can mess around with the numbers as much as you want, and at the end of the day, you will make it to the point that the basic number of electrons that we need would be 12 electrons. So in order for us to be able to perform this reaction safely, we just need 12 electrons. All right? Okay. So in order for us to have 12 electrons, how are we gonna get that from oxygen? Well, we've agreed that each oxygen atom contributes with like one oxygen, two negative, contributes with two electrons. We actually need 12 electrons. So if we do the scissors move, we will realize that we need 6 oxygen anions, right, in order for us to be able to complete this reaction. So here we're going to have 6. So 6 oxygen anions, what are they going to do? They are going to lose 12 electrons. Here we go. And end up forming O2 gas. Is this balanced? No, it's just missing one thing. So we have 6 oxygen anions or 6 oxygen atoms, and we end up here with 2 oxygen atoms. So we are just missing the balance here. So we just need to multiply on this side here by 3. So again, 6 oxygen atoms, 6 oxygen atoms, 12 electrons, 6 multiplied by 2. So we end up having 12 electrons. Okay. Now, this is the oxidation reaction. Let's move on to the reduction reaction real quick. So for the reduction reaction, we've agreed that aluminum would be the cation that's going to be gaining the electrons. All right, we've agreed that we have how many electrons that are contributing to this reaction after doing the math, after calculating it, after memorizing it. We have 12 electrons. All right, so after the aluminum gains 12 electrons, we are gonna end up with the thing that's actually brought us here in the first place, which is just having aluminum. That's the element that we have been trying to extract all along. Now, is this balanced? No. Why not? Simply because if we take a look at aluminum, one aluminum cation can actually gain 3 electrons, and we here have 12 electrons. So how many aluminum cations do we need? We do the scissors move, 12 multiplied by 1 divided by 3, we end up having 4, right? 4 aluminum cations. So we just need to add 4 in here. So 4 multiplied by 3, that's 12 electrons. And we have 4 aluminum atoms, so we need to end up with 4 aluminum atoms as well. Let's just notice one more thing here is that aluminum is a solid, oxygen is a gas, so don't forget the status of the matter. And of course, those are ions coming from a solution of molten aluminum oxide with cariolite. So this is aqueous and this is aqueous. All right, and now we are actually done with the half ionic equations. Let's just recap them real quick. At the anode, we have oxidation. Oxidation is loss of electrons. We have 6 oxygen atoms. Each one is losing 2 electrons. We end up with 12 electrons and 3 oxygen gas atoms, or oxygen molecules to be more accurate. At the cathode, we have reduction, so we have gaining of electrons. So we have 4 aluminum cations in here, 4 multiplied by 3, so those will consume or take those or gain those 12 electrons and end up giving us 4 aluminum metal in a solid state, right? Now we are just missing one thing here, which is the overall reaction. So let me just write that down. I didn't really mean to do that. Let's just write that down right here. Give me 1 second. All right. So that would be our overall reaction, which is basically adding up the two reactions together. Those 12 electrons, 1 second, let's make it in green. Those 12 electrons here were a product and here a reactant, so they came out and then they were consumed here, so they are not going to make it to the final reaction. So what are our reactants? We have 6 oxygen anions or 6 oxide anions, aqueous state, plus 4 aluminum um, anions as well, 3 plus, also in aqueous state, and I really should have cleared those 12 electrons, because as I said, they are not going to make it to the final reaction. Let's get rid of those. 1 second. Okay, here we go. And for our reactants, we have 3 oxygen atoms, which are going to be causing some trouble in a second, and I'll let you know why. And 4 aluminum atoms in a solid state, which is the product that we have been looking for all along. Because if we recall from a few minutes ago, the title was extraction of aluminum, which is Al, and that's what we have been trying to extract all along in the whole Herald process. Now, I just mentioned that those oxygen atoms are going to be causing some issue. Why? If we get back to the cell here, as I said, those are made of graphite. The anode and the cathode, those are made of graphite. So at the anode, we have oxygen forming in here. So that oxygen actually goes ahead and reacts uh, with the graphite anode made of carbon and forms carbon dioxide. And this causes the electrodes to erode, which is why we need to change the electrodes every now and again, because the final product of the reaction is the oxygen, and the oxygen actually reacts with the electrode, with the graphite electrode, and it's very important to mention that it's a graphite electrode, leading it to erode, and that's why we need to change the electrodes every now and again. And it would be really great if you also write down the half ionic equations and the full reaction equation in your answer, just um, to strengthen your answer. That would be really great. So I believe that's pretty much enough for today. Just to recap what we talked about the extraction of aluminum using the whole Herald process. We talked about the cell, we talked about the cathode, the anode, um, talked about bauxite, which is the aluminum ore, how we get rid of the um, iron oxide from that ore by reacting the bauxite with sodium hydroxide, and then the separation technique that we use to get rid um, of the iron oxide would be filtration. This is very important. And then in order for us to further purify the sodium aluminate or the NaAlO2, we react it with carbon dioxide. That's something we're chemically treated with carbon dioxide. That's another thing that's really important in order for us to get pure aluminum oxide. We take the aluminum oxide and add some cryolite to it, which is sodium aluminum fluoride, NaAlO2, and Na3Alf6, and we broke down the structure for that and for the sodium aluminate. What's the point of the electrolyte? It is to reduce or lower the melting point of aluminum from approximately 2000 degrees to around 900 degrees centigrade, save energy, and help with the conduction of electricity. We talked about the half ionic equations, the full ionic equation, and the effect of oxygen that's forming on the electrodes. In the next video, hopefully that one will come out soon, we're going to talk about the refining of copper and electroplating. Before I let you go, just a couple of things. Aluminum is used in so many things like making drinks cans, food cartons, cooking foil, and aircrafts, of course. So those are some of the uses for aluminum, just to keep on the top of your head. Another thing to keep on the top of your head is, for the full reaction to remember that we need 12 electrons just to save yourself some time. Thank you so much for watching. Please don't forget to subscribe to the channel, like the video if you like it, and if you have any questions, drop them in the comment section below. Thank you so much, and I will see you guys in the next video. We will most likely be talking about electroplating and refining of coppers, and we'll end the chapter with the fuel cell. Again, thank you so much, and take care of yourselves.